Well, thanks for the invitation, and I can see that I have a rather mixed audience. So, judging the level right would be hard, but I'll do my best. Right, I'll try and make sure that at least you sort of get what this is about, even if some of the technical details, which I'll try to keep to a minimum, may be beyond your current pay grade, if I put it that way. Right, but that's something to work towards too. So the first slide, my cover picture, is actually a fake. It looks like something very ancient, but this is in fact from fairly recently, 18th century. It's a French woodcut, but it does illustrate something which is central to the whole conundrum of cosmology, which is that cosmology is supposed to be a explanation or description of the universe as a whole. And you can see that in the Middle Ages, people wondered if there was some limit to the universe, if there was some edge to it, then what happens if you stick your head through the edge? I mean, are you in the universe? Are you out of it? If there is no edge, if the universe is infinite, that creates the famous paradox which was ascribed to Olbers, the idea that the night sky should then be as bright as the surface of the sun, because in every direction you should see somewhere, however far away, a star that blocks your line of sight. And that, of course, is not what we see. We see the sky as dark. So basically, went round and round, and we finally formulated a model of cosmology which holds now and which we call the standard model. But I want to start by reminding you that this is nothing new. There was a standard model of cosmology which held sway for about 2000 years. And that goes back in Europe anyway to the ancient Greeks. And of course, there have been cosmological models. Every culture in history has had its own cosmology. And, some of them are 20, 30,000 years old. So what I'm going to talk about as the standard model is by no means new. It's actually very recent. It's 100 years old. And what I want to point out to you is that the last model, which actually worked for 2000 years, or at least was taken by people for granted for 2000 years, was completely wrong, right? It had the universe centered on the Earth, and the planets went around us, the sun went around us, and of course sometimes the planets would go in retrograde motions, and so you have to invent epicycles. And this is the illustration from Dante's famous road movie, The Divine Comedy, where Dante and his muse sort of go through the universe and observe that beyond the planets there is the crystalline sphere, the prima mobile as it's called, and that is where all the stars are embedded. That's why they look like fixed points on the sky. And the point is that we can laugh at this now, but remember that this was the standard model for 2 millennia, right? And nobody dared question it. Why? Because it actually fitted the data. It fitted the data very well. And in fact, it is not really true, as people say sometimes, that they had to invent epicycle on epicycle. I have it from a respected Harvard historian of science that actually only 3 epicycles were quite enough to fit all the data. And in fact, when Kepler's theory came along, it actually didn't fit the data as well as the old epicyclic theory. So why did we get rid of this? Well, that's because there is no underlying physical principle. I mean, there's no explanation for why the planets go around us, why they're in these orbits, why the stars look like point-like objects, why are they far away? You don't know any of that. So the point is that now, if you fast forward a little more, we come to today's standard model, which is called the standard lambda CDM model. Lambda stands for the cosmological constant, which I'll explain in a minute. And this is supposed to be the dominant component of the universe, right? This makes up like 2/3 to 3/4 of all the energy in the universe. And we call it dark energy. And this dark energy is supposed to be fighting gravity and making the expansion speed up faster and faster. So I'm sure you've all read about it in the media, and some of you might know quite a lot about it up to the technical level. But this picture is from the NASA website. So all that has happened is that Dante's picture was black and white, and now we have a color picture. but actually the story it tells is equally fantastic, right? The idea is that the universe is dominated by this cosmological constant. It's getting bigger and bigger, and it will one day become so big that everything will be diluted down to zero. There are people who write books on the ultimate fate of the universe and what a cold, dark death it will be, and so on. And because this dark energy makes up most of the universe, there is very little left for matter, the stuff that we actually understand. This stuff we don't understand at all. But matter, well, about 5% of it is the normal matter that we are made of baryons, well, electrons, whatever, neutrinos. And these are the things that make up stars, planets, the gas between them, and so forth. But uh, about 5 times more matter is in some form that is dark that we only infer through its gravity. So if you put it all in a pie chart, as people like to do, you can see that we, in that sense, only understand about 5% of the universe. We don't know what dark matter is, and we don't know what dark energy is. But there is a big difference, because for dark matter, we can think of possible candidates. For example, we could think of new particles left over from the Big Bang, which might make up the dark matter. And such new particles arise very frequently in theories that we construct going beyond the current standard model of particle physics. But dark energy is a real mystery. I'll explain why, right? But this is nevertheless the standard model of today's cosmology. With this content, and its dynamic is so as to inflate or expand the universe faster and faster. Now, the reason why this model is so popular and has taken over in like 20 years, right, is because it's also considered to be simple. I mean, all the time I hear astronomers describing this model as so simple, it's got only 6 or 7 parameters. Well, that's because they count this cosmological constant as one parameter, although, as I'll explain in a minute, for a particle physicist, it is actually at least 120 parameters. And it fits all the data. Well, so did Aristotle's model, right? It fitted all the data. But this shares this in common with the Ptolemaic and Aristotle model, that it has no physical foundation. We don't really understand what this dark energy is, and it's just a parameterization of a model. Okay, so this is why as a particle physicist, I like to ask, what is really behind this? Is this parameterization misleading us, or is it really telling us something deep about the universe? And the reason why this is an important question is because this dark energy is supposed to be the energy of the quantum vacuum. Okay, 0 point fluctuations in the vacuum. So that's about as fundamental as you can get. And for the astronomers to tell us that they have found evidence of vacuum energy when they look at the expansion of the universe is really problematic, because this is something that we have not at all come to understand in particle physics at all. Nobody in the world, the smartest people in the world, even the string theorists, they have no understanding of what this dark energy is. Okay, it's that bad. So the question is all this for real? So let's ask, how did we come to this astounding conclusion? And for that, I have to take you back 100 years to when the first model of the universe was being constructed. This was shortly after Einstein developed his theory of general relativity. And of course, when you start out, to construct a model and you have no data, they didn't have any data, you make it as simple as possible. Okay. So they assume that the universe is as simple as possible, which means it's exactly isotropic, it's the same in every direction, and it's exactly homogeneous. It is the same at any point. So we call that mathematically maximally symmetric space-time. Okay, and it is described by something called the Robertson Walker metric, which is just a mathematical description which you will recognize. It looks very much like the special relativity Minkowski metric that you know and love, except that this time here I'm actually putting in something called conformal time, which is because the time in this metric is not the time on your clocks. It is the time which is modulated by something called the scale factor. So this metric, the space-time is being stretched, and the scale of the space-time is denoted A. It's called the scale factor, which is a function of time. and I can redefine something called conformal time, which includes that scale factor. Then I can make it look like a Minkowski metric. Now, this is very advantageous because then I can project the entire universe in this conformal time coordinates to just this little patch where we are again at the center of the universe, just as in the medieval view of the universe, right? That's pleasing. And the radial coordinate now is not space, it is this conformal time, or as we call it, redshift, okay? Which means that if there is an object here and emits light, by the time it gets here, the space-time has meanwhile stretched and the wavelength has become longer. So we'll see the spectral lines from this object shifted to longer wavelengths, right? And as you go further and further out radially, the stretching becomes more and more. If you go to a point where it was stretched out a factor of 1,000, the universe was correspondingly 1,000 times hotter then, because the scale factor and the temperature of the universe are inversely proportional, right? So a redshift of 1,000 means the universe was 1,000 times hotter. And if I keep going out, it becomes infinite redshift. The universe was infinitely hotter. So you might wonder what this is all about. Now I'll reveal to you the secret. What you're looking at there is the top of a sphere. We are standing on the North Pole, right? And light can come to us only along the sphere. Light is restricted to coming to us just along the sphere. And the Big Bang is the antipodal point of the sphere. It's the South Pole. So if I put a source of light there, then the light will come to us from all directions along the sphere and it will fill our horizon. So now you can understand in this geometry, how is it possible for a singular point in space-time, the Big Bang, to fill our entire sky? It's because the geometry is not Euclidean. This is Lobachevsky geometry. This is curved space-time. And therefore, it is possible for the entire universe to be depicted like this and for the antipodal point to act like the source of all matter and energy in the universe. Okay. So you can see I could spend the next hour just talking about this figure. There is a lot to take in here, right? But we'll carry on, right? I'm just trying to get across to you that cosmology isn't all that difficult. You have to just realize that your common sense notions of space and time and geometry will can mislead you, because if I tell you the space-time is universe is expanding, you may not ask the question because you think it's a dumb question, but you might be tempted to ask, what is it expanding into? Well, there is nothing for it to expand into. The universe is all that there is. The metric is all that there is. Okay. So since you are students of physics, I can tell you, just follow the maths. Don't ask those questions, right? Because the answers will not make any sense to you. And these are questions that you're asking in natural language. So you can confuse yourself, to any extent possible by asking questions like that. Go with the maths, and then later we'll return and see if we can understand from a more intuitive point of view those questions you're asking. Okay, so this was the geometry, but now we have to have dynamics. And that dynamics, Herr Einstein has kindly provided us. What he's told us is that if I take that metric, which is basically what tells you how to relate space and time, and we can construct objects from it that are called the curvature tensor and the Riemann tensor and the scalar curvature and so on. And I can write down an equation which looks like this, which are Einstein's equations. But this is not just one equation, because these are tensors. They are 4x4 objects, right? And it's actually a symmetric thing. So basically there are 10 independent equations. And what it does is relate the geometry, which is on the left-hand side, to the energy momentum, which is this T mu nu on the right-hand side. So the matter tells space-time how to curve, and space-time tells matter how to move. This was a famous quote due to John Archibald Wheeler. Right now, I know that many of you haven't yet done any of this. You obviously not encountered general relativity. You're not even going to study basic cosmology till your third year, but you get the flavor of how it is constructed. We have to have a theory of dynamics, that's general theory of relativity, and we have to have some assumption for the metric, that's called the Robertson-Walker metric. And when you put these two together, then we get something called the Friedman Lemaitre equations, which are this thing, whole complicated thing, simplifies to a simple equation. Okay, it's so simple. I mean, look at it. It's just a first derivative of the scale factor in time, nothing more complicated than that. So this is like a velocity. We call it the Hubble parameter. And it says that the velocity is determined by the balance between the matter in the universe and something called the curvature of the space-like sections and a cosmological constant. I'll come to that. So what this is saying is that like I've thrown up a stone and there is some kinetic energy of the stone and there is some potential energy and the two have to balance each other. Or if the potential energy overcomes, the stone will fall back to earth. If the kinetic energy is stronger, the stone will go off into orbit. That's what it's saying. Okay. And what we do is we divide this equation throughout by this Hubble parameter as measured today. And then we can write this thing in a very neat way in terms of the energy density of matter in ratio to something called the critical energy, the curvature similarly defined, and the component in lambda similarly defined, because then this whole equation becomes a simple so-called sum rule. Omega matter plus omega curvature plus omega lambda equals 1, right? What could be simpler? So we have managed to reduce the very complicated problem of describing the entire universe into one simple equation. Okay, this is why people love this. Now, let us recall that this is based on these assumptions that we have made, that space-time is absolutely symmetric, the dynamics is governed by general relativity, and there's something I didn't mention, that this energy momentum tensor is so-called dust, which means particles with no pressure, they're just moving without hitting each other. That's what populates the universe. This was the assumption. Now, of course, we know that the universe is not just filled with dust, it's filled with, protons, electrons, what have you. And we also know after this happened in 1915-20, but around the 1940s, after quantum field theory was developed, people like Pauli and so on realized that actually we had to promote dust to quantum fields because all the particles that we know of, they are actually excitations in quantum fields that pervade the entire universe, right? So that's how we think of particles. That's why you understand the duality between the particle and wave nature and all the rest of it. So that, of course, is really the greatest creation along with general relativity of the 20th century, quantum field theory. It's beautiful, but we better believe it. And what it tells us is that this energy momentum tensor that we wrote down here, which normally would have only dust and radiation or whatever in it, also has to have the 0 point energy of these fields in it. And I've noted it here. You don't worry if you don't follow the notation. This is just saying that all the fields are fluctuating in the ground state and they contribute an energy density. And Einstein told us that all forms of energy density couple to gravity, so they will curve space-time. So I must actually take account of that stuff. And what that means is that this cosmological constant, which I've mentioned, this appears on the left-hand side of Einstein's equation because what that reflects is the underlying symmetry. Einstein's equations are covariant, which means that it doesn't matter where you are. It should not matter who the observer is as to what we actually view as physical reality. That is the fundamental essence of it. Okay, and just like you know of Lorentz invariance, which says that all inertial observers should see the same thing, right? And that's how you construct special relativity. If you then promote that concept to curved space-time, then you have general relativity. Okay, it's as straightforward as that. Mathematically, it is not, of course, very straightforward. Einstein had the happy idea as to how to do it, and it works just fine. But we have this problem that when we talk about cosmology, we have to take into account that meanwhile, the description of particles that we developed in quantum field theory, this theory knows nothing about gravity. This theory knows only about the strong interaction, the weak interaction, and the what other interaction is there? Electromagnetic interaction, the oldest one, right? For which, incidentally, we have had a unified theory since the 19th century. Maxwell's theory rules okay. It is absolutely consistent with quantum fields. So we have to now take into account that this quantum field energy will actually act in exactly the same way as this so-called cosmological constant on the left-hand side that multiplies the metric tensor, because this is saying that the equation is covariant. There is local coordinate invariance. So we have to have it there. It's not, Einstein's choice or anybody's choice. It's a symmetry of the equation, and whether we like it or not, we have to put it there. Okay, because in physics, in science, in general, anything which is not explicitly forbidden must be there. Okay, this is what we believe. We have to find some reason why it should not be there, otherwise we can't ban it. So what this means is that this cosmological constant, which actually came from general relativity initially, actually now has components which are adding to it from the 0 point fluctuations of the quantum fields. And so this omega lambda now is the sum of the bare cosmological constant from the geometry plus all the stuff from the fields. And I just told you that this guy and this guy don't know anything about each other, because these are quantum fields that live locally. They're right here. Whereas this lambda is supposed to be something to do with the universe as a whole. The two don't talk to each other, but they add up to make up this overall quantity capital lambda, which is what enters into determining the evolution of the universe. I mean, fascinating, but a real problem. Because that means that if I make measurements in cosmology, I can measure this omega lambda, and that in principle should tell me something about these fields. And indeed, we'll see that that's what has happened, except that the two do not match up. The expectation of what this field energy density should be does not match up with what we actually measure, to about a factor of 10 to the 120. Okay, it's a small error, but that's what we are faced with. This is, Steve Weinberg calls it the bone in our throat. This is the biggest problem, without exaggeration, that there is in fundamental physics, and you're seeing it right here. Now, one thing I forgot to mention is that, God, how do I go back on this? This thing goes into, never mind. That because the matter dilutes as the space expands and the radiation dilutes, but lambda does not dilute. So lambda comes to dominate whenever you come to the, uh, actually, hang on, just give me a second. Let me get hold of my, controls, because otherwise I can't go back and forth. Okay. Yes, I think that should be right. Right, now got it now. Right. So as you saw, we have this metric, we have the equations, and we have this sum rule. Now observe that this matter density is modulated by the redshift q, which means that as the redshift decreases, now we are at 1 by definition. As you go up back into the early universe, this becomes more and more important. This curvature also becomes more and more important, but less so. But lambda remains constant by definition. It doesn't change with redshift. So in the late universe, this guy will redshift away, this guy will redshift away, but this won't redshift away. It will come to dominate. And what happens when you have an equation which says a dot by a square equal to a constant? Okay, the solution of that equation is that a goes as e to the t, right? That's, it has to be an exponential growth. That is the only thing that will give you a dot by a is a constant. Now, that means that the expansion rate of the universe will increase exponentially. And indeed, that's what we find happens when we go back to the equation for the scale factor and we plot it. And we see that if I plot the scale factor as a function of time, at late times, the expansion causes the scale factor to increase exponentially in almost all models, right? So this kind of a behavior, I'm trying to say, is built into the theory. It has to be the case that lambda will, dominate at late times. Now, at early times, this is not true. So for example, when the microwave background radiation decoupled from matter, at that time, the universe was very close to what we call an Einstein de Sitter universe. This is an exactly flat universe with omega equal to 1. Cosmological constant is unimportant. It is matter that is most important then. And this is a perfect description if you go back to a redshift of 1000. So all this stuff is happening today at a redshift of around 1. It is not happening at early times. Now, this, of course, can be determined by looking at data. So, about 25 years ago, astronomers started looking at supernovae, which are stars that go bang. And in fact, I don't know if this animation works. No, it doesn't. The star becomes brighter, the light climbs to a peak, and then it fades off. And you can tell that this is the thermonuclear bomb because the late time light curve actually is flat. It's the lifetime of nickel 56. It is being powered by radioactive decay. But the early time is much more complicated. It is radiation getting out of the star in a very complicated way. Nobody really knows exactly how it does that. But most of the supernovae can be, I'll show you later, considered as standard candles. Like they put out the same amount of energy. So you can think of them as markers of distance. The fainter they look, the further away they are. And what two groups of astronomers did was to look at the supernovae and look at their magnitude, which is how bright they are, as a function of how far away they are, the redshift. And they claimed that when they plotted this, that the Hubble diagram, as this is called, was consistent not with slowing down of the expansion rate, as you'd expect if there was only matter, because matter just gravitates. It actually was showing that the expansion rate is speeding up. Okay. And in fact, what they show here is how it looks when you put us today in the middle of this picture. That if you go back to the past, if the universe had always been decelerating, then it should have been on that trajectory. But actually, it in fact is on a trajectory that is slightly different, suggesting that it initially decelerated but then accelerated. Okay, this is from a Scientific American article or Physics Today article, which shows this.
I want to
Now,
kill myself.
sorry. Oh. To be precise, they are not actually measuring things as a function of time because, of course, they were not back there 8 billion years ago. They measured it just 20 years ago. So what we do is we measure the redshifts and we use that as a proxy for time. So this is not actually a measurement of acceleration. To measure acceleration, you have to measure the velocity at two different points in time, right? That you know. And therefore, you might wonder how can you measure acceleration if you just make measurements at one instant in time? Surprisingly, a large number of cosmologists don't ask this question. They sort of take this as evidence for acceleration of the expansion. But okay, if you buy the argument that I gave earlier, that redshift is a proxy for time, which is a model dependent statement, then you can believe this. Okay. So we have come to therefore believe, and this was given a Nobel Prize, so it better be true, that the expansion rate is accelerating. And what that actually tells you quantitatively is this relationship between the matter energy density and lambda, that this difference is minus, which means that lambda is bigger than matter. Okay. In fact, omega lambda is something like zero point 0.7, omega matter is something like zero point 0.3. Now, that is not the only evidence. There was also evidence from the fact that the microwave background fluctuations, which I don't have time to discuss, tell you that the curvature of the universe is very close to zero. So we are like in a flat universe. Okay, that again deserves a whole hour to itself. But I'm just giving you the pieces of the puzzle. And then there are people who could make estimates of how much matter there is in the universe from various data. This is from the abundance of rich clusters of galaxies. So basically, you have three unknowns, but you have one sum rule. So actually, what you do is you actually measure matter and you measure curvature and you measure this difference. Nobody actually directly measures this lambda, but you infer that omega lambda is zero point 0.7 by using that sum rule. Okay. So it is only because you're using the sum rule that you can work out what omega lambda is. So if I plot this classic triangle plot where each axis corresponds to one of these components, and each point on this triangle is the sum of some value of omega matter, some value of omega lambda, some value of omega curvature, and they all always add up to one. So the statement that is being shown here is that we initially we used to believe the universe was here, then temporarily it moved there, but now we have settled on this universe, the lambda cdm universe, which has, as I said, it's zero point 0.7 in lambda, zero point 0.3 in matter, and that's about it, right? That zero point 0.3 matter includes if a small component. About one-sixth of that is the matter that we know and love. The rest is dark matter. Now, the point is that this lambda is, as I indicated earlier, had been considered to be a placeholder for vacuum energy. So the astronomers have decided that what they have inferred from these observations is vacuum energy, except that when you actually try to compute what the scale of that vacuum energy is, it's worked out from this formula, and it works out to be about a milli electron volt. That's the scale of the vacuum energy, right? You know that what a GeV is, and so this is 10 to the minus 12th of a GeV. So that's about 10 to the minus 3 of an electron volt. It's about the same as the temperature of the microwave background today, right? Now, this is a bit startling because you would expect that if this was vacuum energy, it would be indicating the energy of the vacuum, which is the quantum field theory vacuum. And the quantum field theory vacuum has an energy scale of at least 100 GeV, because that's the standard model of particle physics. Okay, nobody is talking about fundamental physics at an energy of 10 to the minus 3 electron volts, right? There are no quarks and leptons and anything at that energy. So in fact, the scale of lambda is actually in dimensional units. It's actually 10 to the 28 centimeters. It's the size of the universe, because lambda is actually of order h naught square. That's how you get omega lambda to be zero point 0.7. So the present Hubble expansion rate is what is imprinted on the value of lambda that you pick out from the astronomical data. And this vacuum energy business is just inference. This is not something that you have direct evidence for. So, well, I can see I'll have to speed up a bit. So let me go a bit faster. And now it's going to get a little technical for one slide, but please bear with me because this is important. I think this is the point that a lot of people working in cosmology don't appreciate, which is why they think that it's perfectly reasonable to interpret lambda as vacuum energy, and I don't. Uh, and this is because, unfortunately, as you will realize when you are doing, studying physics, it's very hard to find situations where you study both astronomy and quantum field theory together. You have to make a choice. Okay, it's unfortunate because this problem that you're looking at is precisely at the interface of the two. And if we are not equally familiar with both, then you might get the wrong end of the stick, right? Okay, so what I've written down here is the Lagrangian. You know what a Lagrangian is, so you'll take my word for it if I tell you that this deceptively simple thing, which can be put on a t-shirt, you can buy them at CERN, is actually the Lagrangian of the standard model. It describes everything that we know in the universe about particles and fields except gravity, right? I mean, I told you earlier that it is really the greatest achievement of the 20th century in physics. Some people might say general relativity was that achievement. I say both are equal. Okay, they're both amazing accomplishments. Now, what you see here is something. I mean, in notation, this phi here is the Higgs field, and the psi's are indications for fermions, quarks, leptons, and so on. And this F is an indication for gauge fields like the electromagnetic field, the color field, the field of the W and Z bosons, etc. Now, this thing here, this V of phi, is the potential of the Higgs boson, and it is normally written in terms of a Mexican hat. You might have read about this somewhere. But be that as it may, this has been, as you know, actually discovered. This exists. This is not a fairy tale anymore. And we know that this standard model is beyond doubt. It's not a model, it's a theory, right? With our usual modesty as physicists, we still call it a model, right? But it is a theory because, I think this was Manfred Eigen who said this. A theory has to be either right or wrong. A model has a third alternative. It may be right, but irrelevant. Okay. And what I'll argue is that the standard model of cosmology may be in that category. Okay. We're not talking about its right or wrongness, but whether does it apply to the real world we live in. This one certainly does. Now, this Lagrangian, which is so successful at explaining everything, hides a very dirty secret. And that dirty secret, which you should not be told until you're at least doing first year of research, but I'll tell you now, has got two terms which are not renormalizable. They are actually technically called supernormalizable. And they are the basic problem why we think that the standard model is not complete, why there must be more beyond the standard model, right? It's because this term here, which is called the Higgs mass correction, that says that if this Higgs field is fundamental, then as it swims through the vacuum, it actually sees every particle in the vacuum which has mass, because the Higgs field gives particles mass. And these particles, in turn, give the Higgs a mass, it slows it down. And that mass term is written in this form as m squared times phi squared. What is capital M? Capital M is the scale up to which we believe the standard model must work. We already know it works up to 10 TeV. So this scale, if you like to think in terms of distances, is the inverse of 10 TeV, which is, I don't know, something like 10 to the minus 18, 10 to the minus 19 centimeters. Okay. We know that everything works down to that scale. However, according to this term, the Higgs field, which is fundamental, which is truly point-like in this theory, must pick up a huge mass because it couples to every other thing in the vacuum. And we don't find that is the case. We find that the Higgs mass is actually very nominal. It is 125 GeV. And this problem is called the Higgs mass hierarchy problem. And two generations of particle theorists have, bashed their head trying to understand it, and they've invented something called supersymmetry to try to explain it. Compositeness, none of this has worked. We really are currently in a crisis in particle physics, because all these theories predicted new particles which we should have seen at CERN, and we have not seen them. So everyone's running around like chickens with their heads cut off, wondering what the hell is going on, because all the principles that have led us to this beautiful model, this theory, have now, left us in the lurch. Okay, I'm giving you the real gem. This is the truth. We have not given up. This is a challenge. It just means that the solution to the Higgs mass hierarchy problem is something that we haven't thought of. And as you know, physicists like nothing better than a challenge. We like nothing better than to prove wrong a beautiful theory that, I don't know, biologists would give their eye teeth to have such a theory for biology, right? We construct a fantastic theory and then we spend our time trying to prove it wrong. That's just the kind of total, ridiculous people we are. But that's exactly why you can believe anything we say, because we are not trying to cheat ourselves into thinking we have done any more than we have actually done. And nature is the ultimate arbiter. Nature is telling us that the Higgs mass is 125 GeV. This correction is simply not gravitating, so there's some problem. But there's even bigger problem, which is this first term. This first term is the vacuum energy of the standard model. And if this term is of order 100 GeV, as it must be in order to explain why the Higgs is of order 100 GeV, then this term must be 100 GeV to the power 4. But I just told you that the vacuum energy that the astronomers have told us about is 1 milli-electron volt to the power 4. So there is a little discrepancy between the two of 10 to the power 60. Okay. In fact, some people would argue that this vacuum energy scale should not be just the scale of the standard model. It should be raised up to the Planck mass, because that is the scale of gravity. And we are talking here about gravity. So that would then make the discrepancy a power of 10 to the 120. What I say is, if you got a problem of factor of 10 to the 60, you're screwed anyway, right? So let's not worry about 10 to the 120. Let's just accept that this is a problem. This is not something we can brush under the carpet. And in fact, it clearly must be true that this vacuum energy here cannot couple to gravity, because if it did, then the universe should never have got beyond the point where it was about 1 centimeter big, because as it cooled down from the Big Bang, it got down to the temperature of the standard model after about 10 to the minus 12 seconds. And at that time, the size of the universe was about a centimeter. And at that time, this vacuum energy should have kicked in, because all these fields would have been redshifted away. And only the vacuum energy would stand out. And it would then put the universe into exponential expansion. And that didn't happen. Why didn't it happen? Well, Pauli wrote this entry in the Handbook of Physics in 1933, and he writes, as is obvious from experience, the 0 point energy does not produce any gravitational field. So he actually wrote in his notebook, the universe would not even reach to the size of the moon, or something like that. Actually, it would not even get bigger than a centimeter. Now, why Pauli thought that this does not produce any gravitational field, he does not tell us. He did scribble that in the margin, right? But he says that it is obvious from experience, and that is true. If it is, if you are here talking about it, it didn't gravitate. So now you see why this is such a serious problem and why some of us are dead set against the idea that there is a cosmological constant in the vacuum of order a millielectron volt when this number here is at least a factor of 10 to the 60 off. Now, let me make it very clear that this is not a prediction of the vacuum energy. We cannot predict the vacuum energy. We can only guess at its scale. Okay, and this is just a guess. What this says is that if you want to get a milli-electron volt out of the standard model, you'll have to tune the Lagrangian. There are, so-called, well, no, let me not go into technicalities. You have to do something called normal ordering and tune every parameter to 1 power in 10 to the 60. Okay, that's the kind of fine tuning you have to do to explain this, and that is something which is clearly ridiculous. We can understand fine tuning by 1 in 10 or even 1 in 100, right? I mean, let's take a simple example. The mass of the deuteron, the binding energy, sorry, of deuteron is what, 2.2 MeV. That's a lot smaller than the typical mass of a nucleon, which is a GeV, right? How is it that you have an object of two nucleons are bound together with a binding energy, which is, 1/100th of the mass? It has happened. Such an object exists, right? So it is fine tuned. A deuteron is fine tuned, but it is not terribly fine tuned. We can understand that, we can consider that to be still natural. But this power of 10 to the 60 is not natural. Okay, so I see that I've already used up most of my time, and I'm therefore going to sift through the most of my transparencies to tell you why some of us don't believe this dark energy stuff. But first, let me show you something that you will follow, which is that if you do dimensional analysis, you can work out what is the scale, distance scale, that corresponds to that vacuum energy, and that just involves manipulating these parameters which are involved in the problem, and you get the answer that it is zero point 0.1 millimeters. So what this says, and this was actually stated 20 years ago, that there must be some change in the law of gravity at a scale of zero point 0.1 millimeters if vacuum energy actually exists at this scale. So a whole bunch of people started doing experiments with, just like Eötvös did way back to prove the equivalence principle. You take a Cavendish balance, right? And you ask if you can probe gravity down to small scales. I mean, normally you do these things on, large scales, but these guys are so clever that they actually managed to probe the inverse square law of gravity down to 10 to the minus 4 meters, as you see here. And what they do is they put a bound on any term you can allow in addition to the usual inverse square law term, whether the potential for gravitation can have also what you would call in the trade a Yukawa term, something with exponential dependence. And you see what they're constraining is that coefficient of the Yukawa term. And if there was vacuum energy, then this would be the scale it would be at, and the coefficient of the Yukawa term would be of order 1. But these guys have already gone down to a factor 10 below 1 and nothing has shown up. And I'm sure they'll keep trying and they'll go down further, right? But there is a limit to how far you can go. And at some point they'll give up, but they still haven't found what was actually predicted. So this creates a problem that there is no laboratory way to test if this lambda is actually there or not, right? So we have to look to cosmology. And what has happened is that apart from the supernovae, we have looked at many other probes, but let me just come to the supernovae because I want to finish this talk in 10 minutes and not keep you waiting much longer. What we do is when you look at the supernovae, we are doing the following. So let me start here because this is the point at which supernovae, in fact, come up. Okay. So the supernovae are basically, as I said, giant exploding stars. We don't really know what they are. There are many possibilities for what leads to them, but they have these light curves and you can measure these light curves very precisely. And what we observe empirically is that the light curves have weights which are anticorrelated with the peak at maximum. So although there is a lot of scatter, if I put them on top of each other, then you find that they are not actually all the same. Some are brighter, some are less bright, some are wider, some are less wide, but the width and the peak brightness are anticorrelated. So what we can do is we can stretch these light curves to all fit on top of each other using these correlations, which we don't understand theoretically, but they're empirical, so you can use them. So when you do that, you find that in fact they all fall on each other, and we can use them as so-called standard candles, and we therefore can use them to do cosmology, right? And this was all made possible because the astronomers started monitoring the sky with CCD cameras. Because if you are listening carefully, you might wonder, how is it that these guys knew how to measure a spot in the sky 15 days before the supernova went off and it was all dark? Well, they don't. They wait for the supernova to go off, and then they look back in the CCD camera image 15 days ago to see if there was something there. And they see a very faint object, which normally would have gone unnoticed, and they can measure it, right? So that was the technology that made this possible. And this data was finally released in 2014, these measurements of the redshift of the object, the peak magnitude, and some factors determining the stretch and color corrections. So when you take these things, from that you can construct two things. So somebody is entering right now. I don't think they'll understand what I'm talking about. Anyway, so they measured the peak magnitude, which I just showed you how they actually measure it. And you can relate that to these cosmological parameters that I told you about 20 slides ago, right? In fact, you don't actually need a model, because what you are asking for is how the luminosity distance, the distance to the supernovae, is changing in accordance with the scale factor, the rate of change of the scale factor, the second rate of change of the scale factor, and so on, right? The second derivative of the scale factor change is called the acceleration parameter, right? I have to hurry through all this, but the stuff will be on the slides. So when you do that, you find that omega lambda and omega matter, when you plot from what you get from the data, you find that it favors a finite value of omega lambda, as you saw initially, and you can say that the universe is accelerating at some very high confidence. When we looked at what they had done, we discovered that they had done something for which, if you did this in your undergraduate lab and I was the demonstrator, I would fail you. Okay. What they did was to take the difference between what they observed and what the model prediction was, right, which is this quantity, and they square it and they divide it by the square of the uncertainty in the measurement. This part is fine. But then they add an extra uncertainty to each point, which they call sigma int, and they adjust it by hand. So in other words, they adjust the error bars by hand until they get a good fit to the assumed model. Okay. This is what was done to get this acceleration of the universe. And if I explain it to you in the way I've just done, you can see, that this is unacceptable. This is not a principled way of calculating anything. If you knew that that was the right model, then you could use this to estimate the values of the parameters. That would be sensible. But if you don't even know that is the right model, you have no right to assume it. So we got hold of the data, and my master student, a guy called Jeppe Nielsen, and I was in Copenhagen then, said we should use the maximum likelihood estimator. I don't know if you actually learned this. You have a statistics course in undergraduate level, right? So you learned this thing. It was invented by Fisher, and this is the greatest thing that has happened in statistics in the 20th century, how to do a principled estimate of something that you want to determine from the data. So it basically says that you construct what is the probability of seeing the data given the model. It is not seeing the model given the data, right? The two are connected by Bayes' theorem. This is a separate thing. Anyway, I'll not bother with the technical details. We just assume that these distributions are Gaussian because we know how to integrate a Gaussian, and we can therefore construct the likelihood in a completely analytical way. And then we find that these likelihood contours are not up there. They're actually down here. In other words, they do not prove acceleration at better than 3 standard deviations. Now, this is actually a very this was a big result, because normally for a Nobel Prize winning result and a discovery of something, you expect at least five standard deviations, right? You want the odds of it being wrong to be less than 3 parts in a million, whereas this is much more likely than that. So in fact, the precise value of the sigmas is obtained from looking at what the value of the acceleration or deceleration parameter is. So in fact, what we find is that the deceleration parameter is in fact negative, which means that the universe can be said to be accelerating, but there is a large tail which says it is decelerating. So you cannot be confident that we are sitting here and not there. If you do an experiment enough times, it might turn out that actually the true answer was here, right? So the actual probability that the confidence with which you can reject a non-accelerating universe is 3.7 sigma. Sorry, it's the other way around. The probability with which you can reject a decelerating universe is only 3.7 sigma. Now, we did something last 2 years ago, which is more interesting. We said, look, when you look at the sky, people think it is, sorry, people think it is uh, isotropic, but in fact, when we look at the cosmic microwave background, it is not isotropic. It shows that one half of the sky is hotter and one half of the sky is colder, and the temperature varies from one to the other as so, right? Now, this is believed to be due to our motion with respect to the cosmic frame, in which the CMB is truly isotropic. Why are we moving? The claim is that something nearby, is pulling us. I mean, after all, this Hubble expansion does not start until you get to large scales. On small scales, Andromeda, for example, is falling towards us. It is not going away from us. So you'll expect deviations. And what you are seeing is a local deviation from the Hubble law, which says that we are actually going in some particular direction towards this direction at about 370 kilometers per second, because that will give rise to a 1 part in 1,000 temperature difference from special relativity. Now, if this is so, then we can try to make sense of it, as I said, in terms of some local inhomogeneity. But then I would expect that if I go beyond 100 megaparsecs, then I should converge to this cosmic microwave background frame in which the universe does look isotropic, right? And a lot of people say, yes, that's the case. When you count galaxies, we see that the universe is becoming homogeneous. Well, we said if that is the case, then is the acceleration that you infer from supernovae also isotropic? And the answer is no. When we allow for a direction dependence in the acceleration, we find that it is largely a dipole and with a very tiny monopole, which is actually consistent with zero at just 1.4 sigma, whereas it is a dipole with a value which is much, much larger. I mean, this scale is stretched out for clarity. It's actually about 50 times bigger than the monopole, and it excludes the standard model at 3.8 sigma. Okay. You might ask, why had nobody done this before? Well, nobody had. Okay, they had not looked at the sky distribution of the supernovae and just asked the question: is the deceleration or acceleration, that you inferred, independent of the direction? The answer is it is not. It is dependent on the direction, and the significance of this component Q naught, which is being negative, is marginal. It's only about 1.4 sigma. And what that means is that you cannot interpret it as a cosmological constant, because a cosmological constant by definition has to be isotropic. It has to be the same in every direction. It's a property of the vacuum, right? You're not violating isotropy in the vacuum. So this we only determined about 2 years ago, and we have published it, and people simply don't want to know about it. So he decided to go further and given that this dipole is pointing in roughly the same direction as the CMB dipole. I mean, this is not determined with the same accuracy that the CMB dipole is, but they are consistent, right? And in fact, they're in the direction of a local bulk flow. So we think that it's a general relativistic effect. It's an effect of the fact that we are not really co-moving observers, ideal observers, uh, as we are normally taken to be. We are actually moving in this local bulk flow. And if you make a correction for that, then it looks like the expansion rate is accelerating. This was pointed out by a relativist called Christoph Sagas, and we think that Sagas's prediction that the acceleration will be anisotropic is in fact consistent with the data. Okay, so now let me come to my punchline, which is, well, before that, I want to mention that another group did the same exercise using clusters of galaxies which emit X-rays, and they also published very recently, and this also made headline news. They find that there is a very similar anisotropy in a bunch of X-ray clusters, which are at similar distances to the supernovae. So this is the direction in which we saw the dipole from the supernovae. They are seeing a dipole from the clusters in a different direction, but there's a whole bunch of dipoles that are roughly in the same direction as the CMB, which is the star. Okay, so there is something going on here. They're not randomly distributed on the sky, they're in roughly the same direction. Now, the punchline is that this means that you have to go back to the fundamentals of the Friedman, Robertson, Walker, Lemaitre models. And that was a test which was proposed by George Ellis, who is a famous relativist from South Africa, and John Baldwin, who was at the Cavendish lab in Cambridge, radio astronomer. And they said there should be something called aberration, which, as you know, our own astronomer Royal Bradley at Oxford, he came up with this. What was that? 200 years ago. That if you are actually in a moving frame, then a star will not appear to be where it actually is in the sky. It will appear to be slightly moved from its real position. And that will depend on with what velocity you're moving. Now, this is actually a special relativistic effect. Bradley simply discovered it earlier. Now, what Ellis and Baldwin pointed out is that the same aberration effect should happen for any distribution of sources on a sky, as like the cosmic microwave background, it's photons on a sky, but you should have the same effect with a distribution of objects at distant sources. Technically, you have to take account of the fact that the sources don't have a spectrum, which is a black body spectrum. They have usually a power law spectrum. So when you're moving, you are also going to get a Doppler boost of the photons, and you have to allow for that. And there's a mathematical way of doing that. And you get a simple formula which tells you what sort of dipole you should see in the distribution of objects. So let me very quickly show you what you need to do this test. You need some objects which are at a redshift, which are very far away from us. So at a redshift of order 1, actually anything beyond a few hundred megaparsecs should do, because by that time the universe is supposed to have become homogeneous by that scale. So you get this distribution of objects and you look for a dipole, which means that you pick a direction that defines a hemisphere in the front and in the back. You count how many there are in that hemisphere. You count how many at the back. You turn your direction randomly. You do the exercise. You do it 10,000, 100,000 times, and you can then construct a plot, as we did with all these radio sources and galaxies. You can construct this curve on the sky. Okay, and you can see that the actual data, this is done with radio sources, actually follows exactly the curve that you expect theoretically. The scattered is because of short noise, because we don't have as many photons as there are in the CMB, but we have close to 800,000 radio sources, and they give you this. And the direction is actually the same direction as in the CMB. This is plotted in different coordinates, but it's the same direction. It's within 10 degrees. But there is a problem. This dipole is a lot bigger than the dipole in the CNB. Okay. In other words, the rest frame in which the radio sources are isotropic and the rest frame in which the CMB is isotropic is not the same rest frame. Now, we were very impressed by this result, but then we actually did a Monte Carlo simulation to see how often did you get this by accident. And the answer is, well, the chances that we are really rejecting the null hypothesis, the standard model, is 99.75%. That sounds very impressive. But actually, in terms of sigma, that's only 2.8 sigma. It's not a big deal. Okay. For a particle physicist, that is not a big deal. So we can have to do better than that. And that is something that we have just done. We have put out this thing just a few weeks ago. We constructed a catalog, and these are all my collaborators who are named here: Nathan Seacrest, Mohammad Ramiz, Sebastian von Hausegger, Roya Mohai, myself, and Jacques Collin. So there are astronomers, relativists, high energy physicists. We are a sort of mixed bunch. That's why we have between us the expertise to tackle this problem. And we have constructed a catalog of over 1 million quasars on the sky. We block out the galactic plane because you don't want contamination by some nearby object which gives you a false dipole. And actually, the distribution of redshifts for these quasars, as you can see, is well beyond one. 99% of them are beyond the redshift at which there could be any complication. And what we then do is we run simulations of what the dipole should look like. And this is the cosmic microwave background dipole. If the quasar dipole were to be the same physics, then it should be the median value should be here. Okay. But you can expect a distribution. With any measurement, there is always a distribution. However, what we actually measure is nowhere within the distribution. It is way out here. And we can therefore reject the standard model, the standard hypothesis, with a probability p-value of 10 to the minus 4, which is 3.9 sigma. Okay. In fact, we have now tried reducing this cut. And when we reduce the cut, this goes up to 4.4 sigma. We haven't yet reached the magic 5 sigma, but we are getting there very soon. In fact, I have to say that, it's almost like you're afraid of opening Pandora's box, because if you reach 5 sigma, then you will have to accept that there is something very, very fundamentally wrong with the standard cosmological model, that it cannot even give us the correct answer for quasars as we infer from the microwave background using a formula due to Bradley. Okay, I mean, you can't get more retrograde than that. So let me come to the conclusions. There are many other arguments for cosmological constant, which I'll skip over, but I'll take questions on that. So the summary is that the standard model of cosmology was actually established 100 years ago. Okay, at that time, there was no data. In fact, we didn't even know that we lived in a galaxy. Okay, that came a little later. And its foundations have therefore never been tested, right? And we are doing that now. We are not just measuring the parameters. So what we have found is that we have a bulk flow locally, which I didn't talk about, but that's some other work we did. And this bulk flow is actually going much deeper than the scale at which the universe becomes homogeneous. So in fact, we think that this inference of acceleration may be just some artifact of this bulk flow. It is not due to a cosmological constant. Now, that does not solve the cosmological constant problem, because the problem still remains, why is the cosmological constant not gravitating? We don't know the answer to that. That's the biggest problem in fundamental physics. But at least we are not creating a second problem, which is, why is the cosmological constant just sufficiently important today to drive the expansion of the universe at 10 billion years? That problem we don't have. Right? And now we have found that the rest frame of distant quasars is not the same as the rest frame, it is the same, is isotropic, which means that the whole fundamental basis of this Friedman-Lemaitre models is itself under question. So I have not been able to tell you, the title of the talk was Beyond the Standard Model. I have nothing to tell you about where we go beyond the standard model, except that we had a standard model for 2000 years, at least in Europe, which we threw away. Okay. And now maybe it is time to do that again. And G. Naylor, who is just entering the waiting room, is not going to know the answer. Thank you. I think I'll stop there.
Thank you so much. I mean, it's difficult when everyone's muted. All right. It's difficult when everyone's muted to get a clap from everyone. But
they can raise their hand if they want to ask a question, maybe, and then you ask them in turn.
Yeah, exactly. So basically, unmute yourself if you want to ask a question, and that's usually the simplest way.
Thanks. Looks like I overdid it.
I can start the ball rolling. So I haven't done any like QFT or like quantum field theory. But I was under the impression that like general relativity and sort of quantum are kind of, there's like a fundamental problem, right? Because in quantum you can have entangled states, but that's like fundamentally not a thing in relativity, because you need like light, like a finite time to communicate between different places. So how? like how can
Yeah,
you?
yeah, absolutely. Well, I think I know what you're getting at. There is
Yeah.
a fundamental incompatibility between general relativity and quantum field theory. This is, you're
Hmm.
quite right, right? So that is why we don't have a theory of quantum gravity,
Okay.
right? But I'm talking about classical gravity. What we
Okay.
have
Thank you.
now is a quantum theory of the fundamental forces except gravity,
I
right?
see.
So it is, we are describing particles as excitations in quantum fields. And each of these quantum fields has a 0 point energy. Pauli was actually worried about the 0 point energy of the electromagnetic field. Forget about, the weak interactions or strong interactions. So the question then is, if there is this 0 point vacuum energy because of all these fields fluctuating in the ground state, right? Then does that energy have any manifestation? Is it something we can measure?
Mm.
And you might think to yourself, hang on, isn't Casimir energy some effect due to vacuum energy and so on? Those is no, that's the point is, does it couple to gravity? Because according to Einstein, the energy density that enters this equation here, right? This T mu nu here, any kind of energy density will gravitate, including kinetic energy. That is why in general relativity, even the pressure of a gas will gravitate because pressure is just kinetic energy, right? So
Mm.
Einstein says that all forms of energy density must couple to gravity. So if you
Mm.
accept general relativity and separately the standard model, right, which is so you have a classical theory of gravity coupled to a quantum theory of uh, 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 the
Yeah.
interaction, other interactions, and at the interface of those, there is this problem, the cosmological constant problem. Now, many of us are hopeful precisely that construction of a quantum theory of gravity will shed light on how to solve that problem.
I see.
Okay, we
Yeah.
don't have that theory. So as I said, many of us had our hopes set on string theory, which purports to be a theory of a quantum theory of gravity, and it is. But string theory so far has been formulated only in flat spacetimes. In other words, without taking the effect of the energy density on the background into account. So it cannot answer this question. I mean, as presently formulated. In principle, a quantum theory of gravity should answer this question. But no other competitor to string theory has even come close. So, it's a very hard problem. I mean, I'm not trying to say that anybody is at fault. It's just a very, very hard problem. But the good news is that there is stuff left for you guys to do. Everything has not been solved.
Yes, that is good news. Um. Yeah.
I've got a question.
Yeah.
Yeah.
When you say we're moving in a bulk flow,
Yes.
does that mean that our section of the universe is moving? And if so, what are we moving relative to?
Okay. So let me put it this way. We find that when we actually look at, for example, the distribution of supernovae on the sky, we see a dipole in the supernovae in the velocities, which is in the same direction as the dipole in the cosmic microwave background. So what we actually
Mm-hmm.
did was we did tomography. We took redshift slices of the supernovae, and for each one we construct a velocity vector. And when we put them all together, we see that we are moving with respect to the supernovae, the rest frame defined by the supernovae, at a velocity of order 250 kilometers per second.
Okay.
Now, this could be because there is a lump of matter which is pulling us, because the universe, I think I have a picture of that somewhere, let me bring that up, is actually very, very lumpy. The universe does not at all look like a homogeneous isotropic universe. Okay. This is what the real universe looks like in our
Mm.
neighborhood. Okay. So we are at the center of this picture. This is the direction in which we are moving as the CMB dipole indicates. We are part of the Virgo cluster. We are actually falling towards Virgo. And Andromeda, which is very close to us, which is not shown in this picture, it's too tiny, is falling towards us. Now, what we are saying is that we also seem to have a bulk motion in this direction. And initially, it was thought that we are moving towards a particular cluster here called Shapley. Maybe I'll make this thing bigger so you can actually see it. You see this Shapley supercluster? cluster.
Yeah.
It was thought that this is what was pulling us. It was called the Great Attractor. We come up with nice names for these things, right? But what we have done is we have actually gone beyond Shapley now. And if Shapley was the source of everything, then on the other side, we should see stuff falling in towards it. And we don't see that. We see this bulk flow extending out beyond Shapley. Okay. And oops, this was a different illustration. But my point is that because we are going beyond Shapley and we still see this bulk flow as continuing,
Mm.
we can conclude from that that something is still pulling us. We have not yet converged to the reference frame in which things look isotropic, right? And in fact, there is some recent data which I wanted to show you to make the point. Trying to find where that is. Oh, yes. This is a plot that shows what our local flow is, velocity in kilometers per second, versus the radius, the scale over which you're doing some averaging. It's a very complicated and technical plot, but just focus on this dotted line, which is the rate at which the velocity should fall off as we go to larger and larger scales, because the universe is becoming more and more homogeneous. So there is no extra lump to one side to pull anything. The data, this was our data. There is a recent data from something called the 6-degree field galaxy survey, and that is this red point here, and it is very discrepant. We seem to be flowing much beyond the scale at which the universe should have become homogeneous. And it is this that I'm calling the bulk flow. Sorry, I had no time to explain all that. It's rather technical. So that is
Mm.
why I just summarized it as we are in a bulk flow.
All right, thank you.